morning, guys. So this is from Stockvilla Engineering. So I'm going to be running a short structural engineering crash course today, and then we'll be talking on lap length and lap zones for structural members. So the motivation behind this class is my recent experience on sites, and then I thought it wise to do a little research on it, do more research on it, and then teach. I said, let me share it with my guys. Okay, so your host will be Emmanuel Victory, Engineer Emmanuel. So we are going to be talking about what are lap lengths, what are lap zones in structural members. So basically, the structural members we are going to be looking at we're going to be looking at beams, columns, and slabs, right? So those are the major structural members we have in our structures. So we're going to be looking at beam, column, and slab. Where should we lap our reinforcement in our beam? Where should we lap our reinforcement in our columns, and where should we lap our reinforcement in our slab? So these are very critical, critical information. So we're going to be looking at it. So you don't just lap reinforcement anywhere on your structural member, right? So they have specific locations where you lap it for effective quality of our structural member. So first of all, lap length refers to the minimum distance required for two overlapping bars in a reinforced concrete structure. It ensures the load is effectively transferred from one bar to the other, providing sufficient bond strength and preventing slippage. So this is like the definition of what is lap length. So we know what is lap length now. So now in we all agree that basically in structural engineering our structural members have basically two major zones. We have the compression zone and then the tension zone, right? And then we know that concrete is weak in tension and has more strength in compression than tension. And then we also aware that the tensile strength of concrete is 1/10 lower than the compression strength. That means if if a if a concrete structure will be able to withstand a load, be able to carry a load of 10 kilonewton in compression, the tensile stress should be 1, since the tensile capacity of the particular structural member is 1/10 times the compressive strength, right? So concrete has more strength in compression than tension. So the reason why we basically reinforce our concrete system is because of we are preventing it from tensile failure, right? Okay, now so let's check. So below here I wrote these are the lap length for structural members. So for beams, we lap our reinforcement at 60D. 60D is the length of the length of lap now for our beam structure is 60D. 60 is a figure, and then D is the diameter of the reinforcement you are using. So if you are using a reinforcement of 12 mm, so your lap length will be 60 times 12. If you are using a reinforcement of let's say 25 mm, your lap length will be 60 times what? 25. So and so on and so forth. So same too for slab, 60D, and we have the same thing too for columns. Columns is 45D, right? So I stated under that laps are generally provided in the areas with least bending moment. So basically, the areas we provide laps for our structural members are the areas with least bending moment. So those regions in the structural member where we have minimum bending moment are the place that is advisable for we to produce laps. So further, we're going to be moving on to beam lap zones, right? So where are the zones in a beam that we should lap? So we're going to be considering a continuous beam with two spans, right? So a continuous beam with two span. So like I earlier said, I said the beam lap length is 60 times the diameter of the reinforcement bar. So now in a beam, we have two major zones in our beam structures. We have the compression side and we have the tensile side, right? So the tensile side of the beam is under and the compression is on top. So that means we need to focus when we are putting our reinforcement. We have that's why we have more reinforcement at the bottom of the beam than at the top of the beam. So we are not talking about reinforcement now. So let's talk about the lap length. So where in a beam should we provide laps? Like where is it advisable to lap your reinforcement in a beam? Let's say the beam is long, the continuous beam exceeds 12 meter because the length of steel in the market, the maximum length is 12 meter. So now it exceeds 12 meter, and then you need to cut another extra bar to lap it so you can be able to achieve the desired length. So where can we lap our reinforcement in our beams? So if you look at the beam structure, on top of the beam, the compression side, you see they wrote L over 3, L over 3, L over 3, right? And then if you look under, you see where they wrote close to the supports, L over 4, close to the support, L over 4, close to the support, L over 4. So this L over 3, and then you see where there's an arrow indicating the middle L over 3, where he wrote lapping zone for top bars. So it means that if we want to lap our beams for the top side now we are talking about the compression side. It means the lap will be around the middle of the beam for the top bars, right? So the lapping for our beams will be around the middle side of the beam. It will not be to the left, it will not be to the right, it will be at the middle, right? Because that is at the point where we have least bending moment, right? You know that from the right, close to the right, we have a fixed end moment. We have those fixed end moments there. Close to the left too, we still have fixed end moments there, right? But in the middle, the moment there is very minimal, if not zero, most times. So that is the point where we lap. So the trick is, if you're introducing laps in your structural member, you introduce laps in the place that has the least bending moment, right? So now let's check for the bottom bars. So the bottom bars, you have L over 4 to the left, L over 4 to the right. And then you notice for the lapping zone for the bottom bars, sorry, they wrote lapping zone for top bars. I think it's a mistake. It's actually supposed to be for bottom bars. So the lapping zone for bottom bars is close to the support, right? Like L over 4 times the length. That is where the lapping zone is for the bottom. So for the bottom bars, the lap length is the lapping region, the zones where you can lap it is close to the support, and then for the top bar is at the middle, right? So these are the little basic details we need to look out for when we go out for slab inspection on our sites. So now we're going to be looking at the lapping zone for slabs, right? So if you look at it, observe that the bending moment diagram of a slab is very similar to that of a beam, right? So basically, when you're looking at reinforcing in a slab now, you're looking at reinforcing the place that has the least bending moment, which is the same thing. Just that for slab now, we have for slab we have more of bottom bars to top bars. I will show you why. So look at the bending moment diagram here now, right? We have the support, we have the slab, you can see the load being applied on the beam, and then you can see the bending moment diagram on top. So basically, we introduce reinforcement to where we have introduced our reinforcement to where we have moments, right? So let's start from the left hand side where you have that X on top. You notice you have a fixed end moment there. The moment comes and then moves to the midpoint of the beam of the slab, and then because of that, because of a column, you are going to have that fixed end moment in the middle again. See, there's a rise in moments there, and then it came down, and then fixed end moment at the other end, right? So I told you where do we lap our reinforcement? The place that has minimum bending moment. So now we know that slab reinforcement will basically for slabs will reinforce just the compression, the tension zone, which is the bottom bars. So we reinforce the bottom bars, and then we just put top bars for the beams to be able to give it a lot enough stability, right? So now reinforcing the bottom bars, you will notice that towards the support, there's no moment at the bottom bar. The moment there is almost zero. We just have top moment, like moment for top bars at close to the support. But for the bottom side, notice there's no moment. But towards the midpoint of the beam, there's a moment there. That particular period there root positive or sagging bending moment. Notice that curve. That is the bending moment diagram for the center of that beam, of that slab, right? So towards the support, the moment there is zero. Towards the mid span again, the moment is zero. Towards to the farmost right, the moment too is zero for bottom bars. So that is why we introduce lapping at those points where the moment are zero, which is the the leftmost side, the midpoint, and then the rightmost side. Right. Okay, so guys, the next structural member we're going to be looking at is our column. So for our columns, we have that our column we have the two major zones. We call it zone A and zone B. And then from the diagram to my left, you will notice that zone B is where lapping can occur in a column. So for we to be able to lap our reinforcement in our column, our reinforcement must exceed zone A, right? So lapping reinforcement within zone A is not advisable at all for our column reinforcement works. Right, like I said, what is the basis for choosing where to lap your reinforcement? The area with the portion of the structural member with least bending moment, right? So where we have the least bending moment is where it's advisable to lap our structural members. So looking at this column diagram, by the diagram to my right, you'll notice that we have zero bending moment at the center of the column. So we have maximum bending moment at the top and at the bottom. So that's where we now have zone A. So you notice you have two zone A's in the column, which is at the top and at the bottom. And the height of zone A, for you to get, okay, from what is the height of zone A, if you want to know the height, the measurement for your zone A, zone B, and all that. So the diagram to my left gives us the formula for calculating the height of our zone of the individual zones in the column. So for zone A, we have that the height is equal to height divided by 4. So let's say we have a height of 4 meter, right? So 4 over 4, our zone A in this particular diagram will be what? Will be 1 meter. So it means if you want to now introduce laps to this particular column now, our starter bars will need to be up to 1.5 meter high or up to 2 meter high, so that we can be able to they're able to exceed zone A and get into zone B, where it will be safe for we to lap our reinforcement. Right, so it's very important we don't just get to lap reinforcement in anywhere or any portion we choose to on our structural members. The lapping zone are very important, and these are the zones with zero or minimum bending moment for the structural members. So thank you very much for joining me in today's class. We're going to be continuing the next class soon. Thank you guys. Thank you very much.